Good morning, ladies and gentlemen. So today we are actually going to talk about power management. Now, power management, you might wonder actually why it is important in the context of VLSI, because when we talk about VLSI, we only talk about circuits and very deep submicron circuits. And typically these are applications where you have very low power requirement. So why power management is important? That's something we might be all wondering. And so that is the topic of today, that we'll be talking about why power management is important and how we can do power management in VLSI circuits. So as I mentioned that what is power management, why we need to do it, and then in particular we will go to the very important types of circuits which are called inductor based switching converters. So my top lecture will be limited to this. This will be followed by lectures of other senior students on details of some of these circuits. So first, let us try to understand what is power management. As you can easily imagine that, particularly in the VLSI applications, many of the circuits are actually driven by batteries. So a battery may have voltages like 2.5 volts to 5.5 volt, and depending on the condition of the charge, the actual output voltage may vary. On the other hand, we may have to drive loads which will be operating at 1.2 volts, like some of the latest generation microprocessors. They are working at 1 volt, 1.1 volt, 1.2 volts. So we cannot just directly connect a battery and then connect it across the processor, because the processors are actually rated for very low tolerance. That is, if you give a voltage maybe more than 1.2 volts or 1.3 volts, it will simply burn, because these are the breakdown voltages of these devices will be small. And I think the other lecturers must have told you that why the voltage is actually going down to smaller and smaller levels, because mainly to reduce the power consumption. So when actually we are scaling down the voltage, that itself is an indication that we are going in for power management in some way, because with the all pervasiveness of all the digital equipment, all the cell phones, PDAs, cameras, all these modern electronic equipment, consumer equipment, laptop computers, the total power being consumed by all these devices is actually no longer small. And secondly, if you have a battery operated system, then you would like to ensure that for a given charge you can really increase your talk time or the amount of standby time that you can have on your laptop. If you are carrying the laptop on your journey, you would not like to charge it halfway. You should at least expect some 6 to 8 hours of battery backup. So power management is important from that point of view as well. So what do? We cannot just connect a battery to the load, so we need to put something in between. And what comes in between is no longer trivial. There are lots of switches. Firstly, we need to put on the switch only when we need, right? We suppose you are having the cell phone and you are not talking, you would really like the power consumption to be reduced. So you should switch off certain portions of the circuits which are not being used. And then we'll as we shall explain, that we'll need inductors, capacitors, and other components. I mentioned power switches as well, and some suitable connection. The way that we connect decides that whether for a given input voltage, whether we get the desired output voltage or not, right? And all these switches, etc., whenever you need a controller, because when to switch on, when to switch off, and that decision needs to be taken. So this kind of a system where there is some AC input in the form of a battery and then DC output is naturally called as a DC to DC converter. You must have all studied transformer. A transformer is an AC to AC converter, right? And then we make sure that when we take the first year classes, we make sure that we tell you that it will not work on a DC to DC. If you give a DC, a transformer output will be 0, right? So you need really special types of converters which are not in the domain of transformers. So a DC to DC converter is an example of a power management system. right? You have such DC to DC converters in many places. You will have it inside laptop, because you know the external voltage that you will be getting from AC will be first rectified, and you will be converting it to a battery voltage, which is the laptop battery pack. It will be around nominally 12 volts, and then internally, as you know, all these latest mobile processors, they are operating at 1.1 volt. So again, from 12 volt you need to have a 1.1 volt output. So there are lots of stages, and at each stage there are issues like losses, how we can minimize the losses. And if we have losses, apart from the fact that the energy is going wasted, it also heats up the components and on the area in the vicinity of those components. So you know, many of you, if you are putting the laptop on your lap, you will know that it is not really such a comfortable feeling to have a very hot laptop on your lap, right? So this is a big world actually. So power management, everybody is doing power management today. All the big names, and some of them we actually work with, like National Semiconductor, Texas Instruments, uh, Intersil, Maxim. I think one company's name which is not written here, but it does exist, and who do a lot of in-house power management is Intel Corporation, right? You are making, they are making processors. So if you are making processors, you really have to make sure that you do a lot of you know, each part of your processor which has a very high power density, you cannot live without power management. And recent trends in coming up with this dual core, quad core, you know, one of the reasons for this is that if you have just one core, then the power intensity, the density is becoming so high that somebody had targeted that if we do not really separate it out, we will be soon reaching the temperature of the sun at certain points in the circuit. So that's a very dangerous prediction. So people are already aware. So there are 12 core, quad core, quadra core, and all sorts of variations will be there, and so that will happen inside the chip. Right? That's also a power management. We are not talking about that today because we expect that the processor is now a black box, and our job is to supply power to the black box. But the issues are there as well. So worldwide, it's a very large market, and current estimates is about $10 billion, right? Which is not small compared to the fact that the overall semiconductor market is about $250 billion. So just the power management alone, which was actually not even considered as part of the VLSI domain, has already grown to a 10 billion market, and it is going to grow. And some of the companies actually, like say National Semiconductor, Texas Instruments, Maxim, they are more than half the business is actually in the area of power management, and that's the more sort of profit making part of the business actually, because power management requires certain very specialized experience and knowledge, which people need to spend considerable time. They need to have a lot of experience in working with hardware and making sure that the circuit works, because power is something which you have to very carefully control, right? A little bit of loss, even a few percentage loss or few percentage reduction in efficiency will actually can make, heat up certain portions of your circuit, or can there could be certain transients and spikes, and which might destroy your equipment, right? So all these things can happen. So all the companies need trained people in power management. So that's an area for some of you to really look at when you grow up as VLSI or power engineers. And it is a large domain, as I mentioned. In fact, AC to AC, which is a transformer, is not excluded from the domain of power management. But typically, we have when we talk about power management, typically we mean DC to DC, because that's more in the domain of VLSI. But these days, DC to AC has become a big business with home inverters coming in, and soon we are going to have solar power possibly at homes. So solar power will be used to charge our batteries, and then the battery has to be converted to, the battery voltage has to be converted to AC, home AC, and maybe it will be integrated with the AC power supply that we are getting from the grid. So that's an area, and AC to DC has been there all along. In fact, that was possibly the first kind of circuits that came into being after all the battery operated radios and other things came in. So people had what is called as a battery eliminator. So we could plug it into the wall socket and then operate the equipment directly from AC. So rectifier, right, and then AC to AC transformers. And then there are certain subsidiary applications like charging of your cell phone battery or laptop battery. That's actually kind of event that keeps on happening whenever you plug it in to direct AC. Always the battery is charged, so that when you are done, automatically your battery is charged and you can run away with the phone or on the laptop. And then we have also some of the newer types of loads like compact fluorescent lamps, right, which are very energy efficient, and also LEDs, LED based lighting is going to come soon, and some of the, particularly in some of the automotive applications, some of the car batteries, car headlights are already being driven by LEDs. So headlight, backlight, many other things. So because they are more efficient, so people are going in for that, and we'll soon possibly have also home lighting based on LEDs. So these are needs to be driven again through LEDs naturally have to be driven by batteries. So again we will have a different sets of applications which will be actually driving these lights. And possibly we can have a combination where you are actually capturing solar energy and then directly using it to drive those LEDs. So you don't really bring in AC and other losses. You can save certain energy possibly through that. But you still need some matching. Solar panels will give you some voltage, and then you need to convert it to the voltage that is required for the LEDs. Possibly you have to boost up, because each solar cell will be giving you just a less than a volt, right? And then there are associated issues like improvement of power quality. All these new devices that are coming up, particularly even in the AC side, AC grid. There are lots of circuits which are power electronic converters. So when you have converters, it distorts the voltage. It's no longer the normal 50 hertz nice waveform, right? So the power quality deteriorates. Voltage regulation is an issue. That is, you should ensure that voltage is always at 220 volt. So for this also we need to have some kind of power management to ensure that we have quality and other issues are well maintained. Okay, so I have already mentioned this why power management, but just to give you more specific examples, there are a few points which are mentioned here. Maybe you can treat it as a summary of what I've told so far. So DC to AC conversion in homes, then different voltage levels need to be matched, and then we need to have clean power supply, right? Rectified sine wave is not really a good power supply, but you need to have a clean DC which is almost constant. Regulated versus non-regulated, that is, you need to have regulated voltage so that you always get the desired power from your source. And then there are some more issues like source impedance control. So you have also read about the maximum power transfer theorem, right? So from there you can understand that in the matching of the source and the load is very important, particularly in certain contexts. And so how we can adjust that? Source is what we are actually going to design, so it has to be matched with that of the load, right? The source impedance. And then efficiency maximization, like for example, you have solar cells on your rooftop, right? So all parts of the roof may not be getting the same amount of solar insolation, right? So there may be trees, or there may be some cloud cover and so on. So if you want to really maximize the collection, right, you need to do some control on the cells. That is, suppose you have multiple sets of cells and some of the cells are not getting enough voltage, you might like to isolate them from your circuit and capture that part which are more efficiently collecting the solar energy. So all these are coming in the study of power management. So, this example you are all familiar, that is you have a rectified waveform. You have an AC on the left hand side, and through a transformer it goes to a so called full wave rectifier. You are all familiar with this, and then you get this kind of output voltage. But then this is not what you want, right? What you want is actually almost constant voltage. So, what do we do? What we do is a very simple thing, is that we put a so called low pass filter. You know, LC filter is one type of low pass filter, you can have other types as well, but this is the most commonly used one, where if you use a low pass filter here with an LC combination and considering this as your load resistance, then what will happen is that because of the capacitor, the output voltage will tend to be somewhat constant, although whenever the source voltage goes down, you know, because the capacitor will get discharged. So, during that actually the source will be the output voltage will be falling little bit, but as soon as you know the source voltage goes up, again the voltage will pick up. So, that way you will have almost constant voltage across the capacitor. So, this is a very simple filtered output of the rectified sine wave, which can give you a good DC supply. So, another example which I mentioned to you, this is actually how you supply a processor, supply to a microprocessor, and some of them are actually very fast, operating at several gigahertz frequency. So, what happens is that suppose you are working on your laptop and now you have just touched the mouse or something. So, what happens that the system is in actually standby mode, and then once you wake it up, it will demand a huge current, right? Disk drive will ask for some current, the processor itself will ask for some current, because the processor will also go into a sort of standby mode, right? So, all of them will wake up and then they will demand a huge current in a very fraction of a second, a fraction of a microsecond, let us say. So, the rates that are actually currently ongoing are something like this, that about 40 amperes in 0.25 microsecond. That is the kind of demand that these loads are asking from the power supply source, right. So, this is an issue, and then secondly is that the source impedance, you know, which will actually decide on the voltage drop, right. That is also a very demanding value. That is, even if your source has a low resistance of 5 milliohm, right, at a 40 ampere current you will have 200 millivolt drop, right. Now, nominally you are expecting 1.2 volt, and so if you have 200 millivolt drop, then voltage will go down to 1 volt. That is a very large drop. And secondly, how you connect these two is also important. You may not always have a purely resistive connection. Even if you have a simple wire at a frequencies like this, a simple single wire will also be acting like an inductor, inductance. It will have a so called parasitic inductance. So, that will actually reduce the voltage further, and it will also distort the waveform, because whenever you have inductor you will have L di dt across it, and you are talking about di dt of this order. You see di dt is 160 ampere per microsecond. So, no matter how small that the value of L, the inductance is, the L di dt can be substantial and it will bring down the voltage further. So, let us now look at some circuits which will actually work in such demanding situations, and we focus more on the step down converters, because you know, as you have seen, as we have discussed different examples, typically we generate DC voltages which are say of the order of say 12 volt, 5 volt and so on, while some of our loads are actually operating at 1.2 volts or I mean 1.8 volts these days, right. So, step down is a very important task, right. So, okay, so what is so big about step down? Anybody can make a step down circuit using a resistor divider, right. So, if that was the case, of course we can close the class now, right. So, what happens is that there are some issues, there are some difficulties if you have a purely resistive divider. See, firstly, if you have a resistive divider, right, you know that whenever the load is drawing some current, right, you can draw actually the Thevenin's equivalent circuit here. The internal source resistance will be R1 parallel R2. So, whenever current is drawn, the voltage actually falls below V in, or rather the below the open circuit voltage, which is V in times R2 by R1 plus R2, right. So, that is what happens if you draw any large current. So, voltage will can drop substantially. So, another thing that happens is that okay, just go back to that. Another thing that happens is that there will be lot of losses in these two resistors, resistance R1 and R2, right. So, what can we do? Can we improve this situation? What we can try to do is that we drop this resistance and then have a controller, have one resistance R1 and have a controller which automatically adjusts the value of the resistance R1, so that we get whatever voltage we need at a given time, right. Now, how can we do that? We can have it, I will show how we can do that. So, typically one thing we can do is that we can have a transistor whose gate voltage or the base voltage we can control to get the desired drop across this device, and always the exact value of the load voltage that we want, that we can have it across this. And how do you know whether we have the desired value or not? So, what we need to do is that we need to measure this output, right, and after measuring this we compare it with a reference, saying that okay, I want 1.2 volts, am I getting 1.2 volts? So, we can have a voltage reference circuit which will be at 1.2 volts, and then we will compare if there suppose the voltage is more than required, then we actually increase the drop here, right, and if the voltage is less, then we decrease the drop here, right. So, through that we can control the value of the output voltage. But what are the issues? There are some very interesting issues. That is, suppose our input voltage is 5 volts, right, and we want 1 volt here. What do you think will be the efficiency of the circuit? The efficiency will be quite low, because you know a very simple concept I will tell you, that if you have 1 volt here, then you will have 4 volt drop here, right, and these two are in series, right. So, if these two are in series, they are carrying the same current. So, 40% of the energy will be going into this resistor, and for 10% in this case 5 volt and 1 volt. So, 80% of the energy will be lost in this resistance, and 20% only will be going to the load, right. So, you will have an efficiency of 20%. Any other problem that you can think of? The problem is that this resistor, or whatever we have, even if you have a transistor in place, because so much of energy needs to be dissipated through this, it will be heated up. So, apart from the loss, the energy loss that is happening, there is a possibility of heating up the device and possible damages. Well, but still this is a possible solution, and particularly when the output to input ratio is not very low, in the sense that suppose it is of the order of say 80%. Suppose you want to develop say 1.2 volts from a supply of 1.5 volts, possible, there are applications that are possible. Then we can use a solution like this, where you can have a power MOSFET, for example, and that is acting as a controlled resistor, and looking at the output voltage, we drive the MOSFET in such a way that the voltage across the MOSFET is always the difference between the desired voltage and the input voltage. So, we control the output the transistor in this fashion. Now, we come to one different kind of circuit, where we actually try to improve the efficiency compared to what we were thinking, what we could get earlier. Now, this circuit is typically called as a buck converter, right. Now, in what way is it better than the earlier circuit? Let us try to understand. This is actually a switched power supply. You know, in our PCs actually we use these kind of supplies, and we call them as switched mode power supplies, SMPS, right. So, this is called switched mode because there are switches here, and the switches are used to ensure that we get the desired output voltage at the output terminal, the load terminal. Let us look at the basic concept first, is that we have the input voltage, and then suppose we keep the switch on this position, on the top position to start with, right. What will happen? This current will flow through the inductor and through the capacitor. So, capacitor will be charged, and also at that time the load will also be getting a supply, right. And so, let us say that for a period which is suppose we consider one full time period to be Ts, right, and out of that d times Ts, where d will be called as the duty cycle, it is a fraction of the total time period. So, for a period d times Ts, we keep the switch on the top position here, so that at the output we get a voltage which will be equal to, or rather at the switch point here we will be getting a voltage equal to V in. It will be then going through the inductor and there will be some drops, etc., because current will rise and there will be LDI dt. Those analysis can be done that way. But at this point we are getting a voltage which is actually equal to input voltage V in, right. And after some time we simply take the switch, make the switch off, actually disconnect it from that end and connect it to ground. So, what will be the voltage here? Voltage here will be 0, right. So, the switch node voltage, as we call it, V switch, right, with this terminal being positive and this terminal being negative, that will be behaving like this. So, we will have some constant voltage V input and there will be some 0 voltage across this, which will be then repeating. After that it will repeat. Now, what voltage are we going to get at the output terminal V out, right. Now, when you are actually studying this circuit for the first time, it becomes little difficult to analyze, but once we become familiar, we can have different simplified ways of looking at it. And one thing, for example, let us initially assume that, okay, let this output be a constant output, right. Suppose it is a purely constant output, then what would be its value, right. For that we actually can do a very simple calculation, where what we can do is that inductors are actually very interesting devices, right, which actually if you take the equation L di dt, the voltage across the inductor is L times di dt, right. So, you can based from that concept, N and Li is the flux, right. So, L di will be equal to V times dt. So, integral of L di will be the flux that is stored in the inductor, and then voltage times dt will be equal to that value, right. So, since an inductor does not keep on accumulating fluxes over every cycle of waveform, when the circuit is in the steady state, over every cycle of the waveform, the voltage times the time period across the inductor can be balanced. That is, each for over each cycle it will be equal to 0, right. So, from that point of view you can actually calculate that under these conditions the output voltage will be equal to d times the input voltage. Actually, some of the other lecturers, they will be giving the details of how it can be derived. So, output voltage will be equal to d times this, and d has to be always less than 1. So, voltage across the load will be always less than the input voltage. Now, once that happens, and that will be approximately constant, you can approximate to be almost like a straight line, and that will be the voltage across the load. Now, assuming that as a base condition, you can then analyze the entire circuit in a very simplified fashion, because what under that condition the voltages across all the points here. The voltage across the switch node at different instants of time, and the output voltage, right. So, once the two voltages across the inductor, what will be the current through it. The current will rise in the linearly, actually in the first part, where input voltage will be greater than your output voltage, and this part of the circuit in this part of the waveform, actually this point is grounded. So, the current through the inductor will actually go down, right, and then the inductor will be sort of discharged, right. So, with this there is of course some diagrams are here actually what I was telling you verbally. So, during the on period the inductor current will be rising, because there will be net positive voltage here with respect to this. V out is less than V in. So, this terminal is positive with respect to this, and in the subsequent period this voltage will be at a ground 0 and this is V out. So, this V switch will be the voltage across the inductor will be negative in the sense, and then current will be falling, right. And so, current will rise at a rate which will be proportional to the difference between V in and V out, and here it will be falling at a rate which will be proportional to V out. In fact, that is the way you can also calculate what will be the value of the V out. So, in a steady state what will happen is that you will start from some value, you will rise up to some value, again fall back to the value you started with, right. In the steady state it will be a periodic waveform. And so, what is the benefit? What is that we are gaining through this? If we have an ideal switch and the inductors and the capacitor, they are lossless, in the sense that the inductors do not have any series resistance, capacitors do not have series or parallel equivalent resistance, then there is no loss in this circuit. There will be some, practically speaking, there will be some losses in the sense that the switches will not be ideal, inductors, capacitors will not be ideal, but ideally speaking this will be a lossless circuit, right. So, that is the beauty of this compared to the earlier circuit that we had. Earlier circuit what we had a control switch, look at this, we had a control switch, but there will be a drop across this switch, constant drop, right. While in this case what happens is that, look at this, if the switch is here on here, a switch when it is on, right, what happens that ideally the voltage drop across it is 0. So, some current is flowing through it, no problem, the total loss through it will be still 0, voltage times 0 current. And then what happens when we make this off, right, then what happens, then it is blocking the supply, right. That means there is a substantial voltage across it, but there is no current through it, right. So, there will be still again no loss. So, that is the beauty of this circuit, under both conditions it has no loss. So, that is how we are actually improving the efficiency, right. But there are still challenges, you have to make switches very efficient, and that is one of the challenges. In fact, that is the part of the VLSI design challenge, in the sense that these switches, these buck converters, we are these days we have it on chip, the converters are all within a chip. So, these switches have to be realized as a power MOSFET, and you are already familiar with the VLSI, and to some extent maybe the layouts also, that you have to have a proper layout of the switch, so that it has a minimum on resistance, for example, because if unless the on resistance is low, you are still going to have a lot of loss, right. And similarly we need L and C which are close to ideal, that is also not possible. And then finally we need to have proper control of these switches, and the design of the controller circuits which will properly switch it on and off as required, that is also a challenge. And of course, you may say that okay, it is a simple buck converter, so maybe it is not so difficult, but these days there are lots of general cases where you will have one input voltage supplying to 5 different loads at 5 different voltages, each one requiring different amounts of currents, right. So, controlling the switches under that conditions will be a challenge. And then there are also another kind of converter which I will come to, which will be called as a boost converter. It also brings its own problems. So, these are the points, and but all said and done, we do have buck converters which are industrially available, and some of them have been designed in our lab also, which are have an efficiency of the order of 80 to 95%, right, and sometimes even 97% in some cases, special cases it can be achieved. Now, that may not be ideal like some of the efficiencies we get in transformers which are 98% and so on, but when we work in low power mode, efficiency is certainly an issue, but apart from that, as I mentioned, is the losses, right. So, as long as you can keep these losses within control and there is no overheating, that is a reasonably good solution, right. So, we do have these as a more or less acceptable. I mean, of course, if it is more than 90, it is always better. So, these are some of the challenges that are there in this design. And then, as I was mentioning, there is another elder brother of buck converter. Why elder is that it gives you more output voltage, right. So, it is called as a boost converter. And conventionally, boost converters were not so popular earlier, because typically what we used to do is that we used to charge everything from or supply everything from the wall socket, right. Wall socket we used to charge. So, we used to convert it to some voltage like 24 volts, 12 volts and so on, and from there you always used to step down. But these days, there are lots of demands of single cell based applications. Lots of applications are being driven by single lithium ion cell, and tomorrow we are expecting that all of these some of these applications will be driven by single fuel cell, right, which will be a very low voltage output of say 0.6 volt, right. So, in this case actually the requirement is that of boosting up. Another application where this can happen is like say in a car, right. In a car we have 12 volt battery, but many of the engine controls, solenoid valves and so on, they require 48 volt supply. So, you need to boost up, right. You cannot put another battery which is 48 volt, it will not be cost effective, and it also cars also have a problem of space today, right. You are trying to make compact cars, you do not want to put too many devices in there. So, we need to boost up. Now, I am not going into the derivation of how the output voltage is more, but you can look at the expression which will be derived by some of the other teachers. So, here you see again, if you look at a call D to be the duty cycle of this, then what happens, okay, just for a brief explanation is that when you start this, we put the switch onto ground. So, what happens is the voltage, this input supply voltage that drives a current through the inductor, right. So, which is a shorted inductor, that means L di dt will be equal to V in. So, I will be increasing linearly, and then at some point of time we switch this off and put this switch onto the output. Okay. So, then actually the inductor which is already having a lot of current then is used to pump energy into the capacitor. Okay, there is some diode that is required here which is not mentioned here, but that will basically will ensure that if there is no that is, even if this inductor is actually at a this input voltage is at a lower voltage, right, it can still supply current in this single direction, it does not get, current does not flow backwards, right. So, under that condition this will be charged, right. So, we will be getting some output voltage. Now, as it happens, the relationship between the output and the input in this case is output is equal to V in divided by 1 minus D, right. So, if say D is equal to 0.5, then what happens, then at the output you are going to get twice the input voltage, right, and then as you go ahead and D becomes say 0.9, you can theoretically get 10 times the input voltage, right. So, this is the working of a boost converter, right. We will not go into the details of that, towards the end we will summarize some of the possible converter configurations, but we will look at how we can realize a buck converter in a VLSI circuit, right. So, this is a switch, right. Now, ideally speaking, if you have one switch here, right, that should be enough, right. What we can do is that whenever we are putting this back onto this, we can put a diode, right, so that through that this circuit can be completed, right. It used to be called a freewheeling diode. But today actually this is actually era of control. We try to achieve more by proper control, and also when you have a diode here, there is more loss than you would have in a switch like which can be realized with an NMOS. So typically what is done is that this what we call as a high side switch. Actually why it is high is that it is connected to the V in. So the high side switch is typically a PMOS, right. Why it is a PMOS is that when you want to drive it properly, all we need to do is to ground this gate, right. If you have some input voltage here and if you have an NMOS here, if you want to drive it through properly, you need to give voltage which is higher than this V in, right. So it is convenient to have a PMOS here where you get a can ground this, and this switch is typically realized by an NMOS because of the same reason here, right. So this is the way we realize these two power switches, and then we have our L and C, and we have the we try to minimize the on resistance of these switches, so that even when it is on, as I mentioned that ideally if the resistance is 0, then there is no loss. That is of course practically not possible, but whatever is possible is that we try to minimize this, and the layout is done very carefully, right. When you learn more about layouts, you will know how you can actually fill in metals etc. in the all possible spaces in the layout, so that you can minimize the on resistance. And interestingly, actually this switch, suppose it has to carry a current of say a couple of amperes, it is not a single transistor. It cannot be realized with a single transistor. If you want to realize using a single transistor, you will require a W by L, which will be maybe of the order of 1 million, right. So if you have a 1 million W by L of 1 million, and even if a gate length of some say 180 nanometer or something, you will still have a very large W. So what is done is that it is realized in parallel, right, by making number of fingers, right, and it is laid out in 2 dimensions, right. So that is how a switch, power switch is realized, and these are actually called lateral power MOSFETs, right. Those of you who will be studying electrical engineering will be coming across power MOSFETs. Power MOSFETs are actually, you will see that there will be of 2 types. One will be these laterals that we are talking about in on chip realization, and the other one will be so called vertical power MOSFETs, which are used for say 100 volt or 200 volt, 400 volt kind of devices, and which has basically much larger breakdown voltage and much larger capacity. But for integration with integrated circuits, the power MOSFETs are usually lateral, and they are laid out in 2 dimensional fashion. That laying out itself is an art, only specialists can do it. In fact, there are few companies who only do layouts of power MOSFETs, right, and big companies hire their services because they are so good at it. Similarly, the NMOS can be laid out, and typically, as you know, that PMOS has typically less, basically the holes have less mobility, and for the same RDS on, typically we need to have a larger area, and often the PMOS is of the maybe say about 1.5 times that of the NMOS. So that is how a switch is realized. Now coming back to some of the global issues and the way we classify the operation of power management circuits, or how we specify, whether the input voltage is an important parameter, what input voltage it should work with, the output voltage, what is the requirement, what is the tolerance that we can allow, what percentage of tolerance we can have, whether isolation is required between input and output, right. The circuits that we have shown does not have any isolation, in fact they are electrically connected, but sometimes we may have some need for isolation, right. So we need to have a transformer or something in between. Load current requirements, we do not need to understand all this at this moment, but just the issues are being listed out, and they are all in one place. What efficiency is required, what kind of application is required, how fast a current rise you want in your circuit, transient requirements, how fast you want the system to stabilize after a transient, right? There is sudden load has increased, and then how fast you want the system to stabilize. And there are some more issues like which we will study later, maybe in higher classes also, like bandwidth, which will also decide the transient requirements. Then there is another issue, EMI, electromagnetic interference. If you are having the switchings, right? So these inductor based supplies, all that we are talking about, we are having the switching. So switching will also bring in the EMI. So we have to be careful that we don't really disturb the other devices which are in the vicinity, in the same layout, within the same wafer. So then there are other things like board area, cost, and things like that. And we have different options, right? Which possibly is not really in the right time to decide at this, discuss at this moment, but you can have a look at this. That is single level, multi level, single stage, multi stage, single phase, multi phase, and all that. Okay, that could come later. Now, before we end, we will just show you some of the inductor based topologies, right? This is mainly for your record, and we have described both these two already, the buck and the boost, right? So, as I mentioned that in the buck converter, the output voltage is actually linearly proportional to input voltage and depends on the duty ratio, right? And this factor, the ratio between the output voltage to input voltage, is called, if you call it as a magnification factor M. So, in the case of a buck converter, this is equal to D. D is the duty ratio. As duty ratio increases from 0 to 1, almost, of course, exactly 1 means you are really not switching, which is not the right condition, but theoretically under this condition the voltage will be linearly rising. In a boost converter, the output voltage actually the magnification, whenever D is 0, then magnification is 1, right. So, it starts with the magnification 1, and then as you increase the duty ratio, as I said, to say 0.1, sorry, say 0.9, let us say. So, the magnification will be going to 10, right, and then at D equal to 1, theoretically it will go to infinity. Okay. There is another topology which is called as the buck boost topology. We need not go into the details, you can analyze each one as it comes. Typically its output actually goes negative, it's also called an inverting buck boost, and voltage actually is negative and keeps on falling or increasing in the negative direction with increase in duty cycle. There is a topology for non-inverting buck boost where 2 switches are required, and which is actually just the reverse of this, right? And then there are 2 more topologies. One of them is called as a bridge topology, and that is actually centered in the middle, in the sense that at D equal to 0.5 you get no output, and you can actually get a bipolar output. You can get both positive as well as negative output. Similarly, another topology called Watkins-Johnson topology, it also can give you positive and negative outputs, but in a nonlinear relationship. So, with this actually we come to the end of this first lecture on power management, and now I am open to questions. Questions from your side? Yeah. We choose actually a duty cycle which will be giving you the desired output. So, suppose you have 1 volt input and you want to get 2 volt, we set a duty cycle to be nominally 0.5. Just a moment, we will show that. Not moving. This one. No, it's not the, this is not the output actually. You see what happens is that uh, the output is actually decided by the capacitor, right. So what happens in the initial stage, first few cycles, yes indeed the capacitor voltage will be very small, right, but in the steady state what will happen is that this output voltage will be, say suppose this is 1 volt and this is 2 volt, right. Then while this switch is here, the capacitor voltage falls nominal little bit from the 2 volts to say 1.9 volt, right. And then once we put this switch back onto this, then this V in plus LDIDT, which will happen because of the switching, so that will be greater than 2 volts and that will pump in more energy back into the capacitor. So capacitor will lose some charge into the in the first half when during this on this period, right, and then whatever charge is lost during that will be compensated. First period is on period of basically for the inductor. You can say inductor is sort of charged with a voltage here V in and this is 0. So there will be a voltage V by, this will be rising at a rate of V in by L, right. So that is how it will rise. So inductor will rise, current will rise, and then once we put the switch back onto this, then there will be LDIDT plus V in, together will be greater than V out and you will be pumping more energy into the capacitor. Yeah, next question. So yeah. This is not the output voltage, this is the switch node voltage. So output voltage if you draw, let us look at this. So output voltage will be a constant voltage and that will depend on the duty cycle, almost constant. Right, actually we looked at this as a switch, right. This switch actually the condition of this switch, we are saying that when it is here then this is on, and that on period is actually called D, that duty cycle. It is just a convention, it could have been defined otherwise also. Right, inductor current is rising, yeah, that is the common part, you are right. Okay, so thank you very much for your attention.